we looked at the law of conservation of energy, GG. We add the dramatic echoes for Mr. Dueck. I said use it when there's a change in height and a change in speed, a yucky curvy path, but you can use it in other situations. Slingshot questions are nice. I think I like this question. I know I give this in physics 11. I can't remember if I do it in physics 12. Slingshots and bow and arrows are great examples of conservation of energy. Slingshot is pulled with an average force for a distance of 90 centimeters. Of course, the first thing I would do is I would say, nice try, Mr. Dueck. 90 centimeters, how many meters? 0.9. How much potential energy is stored in the slingshot? So we need to realize potential energy is stored energy. Gravitational potential energy is mgh. Am I storing energy in the slingshot by changing its height? Look at the picture. No. So a common mistake, and it's one that bugs me. I see kids, Anderson, they go, oh, he said PE. It's got to be mgh. And then they look down, they steal the mass from there. They say H is in meters. That's a distance, but it's not a height at all. You cannot use mgh. Instead, well, Anderson, what are the units next to this 70? What's that a measure of? What's this a measure of? You know what? I think the other way to think about this is to realize I can figure out the amount of potential energy by going work is the change in potential plus the change in kinetic. Let's assume that the slingshot starts at rest before I start pulling it and ends at rest after I finish pulling it. So its change in kinetic energy, if it starts and ends at rest, is 0. Let's also assume its initial potential energy is 0. It hasn't stored any energy. What I really get is this. Force times distance equals the potential energy. We can call it the potential energy final if you want. Anderson, what did you say the force was? The distance, 0.9. How much work and also how many joules of energy have I stored in this slingshot? My Nerf dart gun works very similarly. I apply a force over a distance when I cock it back, and that's what stores energy in the system. 63 joules, yes? So a nice follow-up would be, if there's a 35-gram mass in the pouch, how fast will it leave the slingshot? It wants me to find a speed. I just found a potential energy. I suspect I'm going to do this with conservation of energy. And I could do the full equation. I could go PE initial plus KE initial equals PE final plus KE final. But I would be fine if you said, okay, now the initial potential energy stored in the slingshot turns into all of the final kinetic energy. If you jumped straight to that, Jacob, I'm good with that, because that's what's happening. You've stored 63 joules of energy in the slingshot. This would be 63, and that's going to equal a half mv final squared. It's interesting because in part A, PEF was 63, but in part B, now we're starting with it pulled and we're releasing it, so it becomes the initial stored energy. How would I get the V by itself? Times by 2, divide by M. Oh, 35 grams. How do I convert that to kilograms? We don't do physics with grams. To go to kilograms, we take grams and we divide by 1,000. So we're going to get this. VF equals 2 times 63 divided by 0.035 and square root. Oh, this might work out evenly. I think it will. I don't know what the answer is, but I think you end up with all perfect squares on the top. So I think, does it work out evenly? 60 even? I just finished marking my physics 11's kinematics test, and the number of them that forgot to square root, even though they wrote the square root, even happened this morning in physics 12. I had somebody raise their hand, 3,600 meters per second, Mr. Dueck. And I said, okay, if you're getting that from a slingshot, that's punching through brick walls. I don't think you're like that is duck and cover and get out of the way. That's about 4 times faster than a sniper rifle. I don't think you are. So don't forget the square root. Technical comment on ramps. The normal force does no work because it's perpendicular to the ramp. Don't write this down. I'm just going to do a quick dollp. Here's the normal force. Don't write this down. What's the angle right here? We said it's 90. That's why it's called normal. If you wanted to figure out how much work the normal force would do, it would be the normal force times distance, but the distance is along the ramp, and so we would put in the cos theta. What's the angle right here? We said work is actually force times distance cos theta. What's the angle right here? 90 degrees. On your calculator, what's the cosine of 90 degrees? Yeah, which means when we're doing free body diagrams to figure out how much work when we're listing our forces, normal force does no work. Also, you can make the same argument for a rope for tension on a rope swing. Don't write this down. If I'm swinging on a rope swing, no matter where the rope is, it's forming a 90-degree angle. So I would have tension up, but it's doing no work. It's applying a force, but it's doing no work because if you go force times distance, cos theta, cos 90, 0. So that lets us handle stuff like rope swings. Example 2, is there a good rope swing in Pitt Meadows growing up over a lake? I never grew up in Pitt Meadows. Is there a good rope swing over a lake somewhere, like on Pitt Lake or anything? Presley's shaking her head. Okay. Not in Abbotsford, but in Hope, there was on Kakawa Lake a really good rope swing. Nice deep area where you landed as well, so you could go drop way down into water. Didn't have to worry about injuring yourself. Someone had put a nice water ski handle on the rope, so it was like you could really get, and it was on a nice hill, so you get some good height. Here, we're going to have Tarzan running. He runs along the ground. He's going to grab a vine swinging into the air. Similarly would be what you see Spider-Man doing when Spider-Man runs and then uses his web. The only issue there is the web is elastic and it's storing energy, so it's not going to be the same equation. Our vine is not going to be elastic. Let's have Tarzan run. Dollp, it says. So here's Tarzan running. We have, let's say, a foot kind of like this as he's sprinting along the ground. He's running. There's my stick figure diagram. Here's the rope swing. He's going to grab it and he's going to swing up. Okay. When Tarzan grabs the rope swing, well, first of all, what does it want me to find? Ella, what does it want me to find? Okay. Did it say how much work? Do you see the phrase how much work anywhere in this question? So I'm not going to use the work energy theorem. I'm not going to go force times distance. It wants me to find a height. Is there a change in height in this question? Or will there be when he grabs the rope swing and swings? Will there be a change in speed? Is there a yucky curvy path? This is a good job for conservation of energy. It's going to be initial plus initial equals final plus final. Then we're going to ask, are any of these 0? Ella, let's think kinetic energy. Is there ever going to be a moment where Tarzan comes to a stop, where he is at rest? Yeah, I think that. Is there ever, let's now look at potential energy. Is there ever a moment where Tarzan's on the ground? Now, I got a bit of a problem with that because I think isn't that my initial height? Don't I need to add Tarzan's height? No, I could. One of the nice things about conservation of energy, because it's a scalar, I can put the ground wherever I want to and just adjust all of my heights accordingly. So yeah, I'm going to put the ground right there. And really what I'm going to find is how much higher he swings. And if you want me to be fussy, I'll add Tarzan's arm height to it later if I needed to. And I get a pretty simplified equation. Ella, what's kinetic energy? How do I calculate that? So that'll be a half mv initial squared, and potential is mgh final. Oh, Ella, is there an m in everything? What does that mean? What does that mean in real life? In real life, it means assuming the vine didn't snap, if Tarzan runs at 8 meters per second or Tantor the elephant runs at 8 meters per second, they'll both swing to the same height. At the rope swing on Kakawa Lake, you would notice because you couldn't take a run at it, you were just lifting your feet because you were starting on a hill and swinging. Little kids and grown-ups, they would all swing out to the same height because the mass is canceled. Okay. What am I trying to get by itself? Okay, I would also have no problem giving you the height and asking what the speed is, but here we want to get the h by itself. I think h final is going to be vi squared over 2. I'm not going to bother writing the 1 from the 1/2, but there's definitely going to be a g on the bottom. You divide by g, yes? Do I need to square root here? Nope, there's no squared on the h. So it's going to be 8 squared divided by 2 times 9.8. This won't work out evenly. What do you get? 3.27? Yeah, doing it in my head, I was getting a little above 3, so that sounds good to me. I wrote here, slap shots are great examples of energy transformations. There's a video. I actually showed you all the video last year. It was from Smarter Every Day, and it looked at why when you do a slap shot, you actually hit the ice behind the puck. And it's so that you flex the stick, you store energy in the stick. I have another video I'll show you a bit later if I fit it in, I hope. I want to get to example 3. I like example 3. You know what? There's going to be a roller coaster or 2 or 3 on your test. Roller coaster below has a mass of 255 kilograms. If the coaster just barely makes it over the first hill at A, how fast will it be going at location B if we assume VI equals 0 and we ignore friction? Joe, what's A asking me to find? Is there a change in height? Is there a change in speed? Is there a yucky curvy path? I'm going to use conservation of energy. I think before I even start, though, I'm going to say I think initial is going to be right here. Final is going to be right here. Since they gave me the picture, I'd probably just label that. Takes 1 second, and now I've gathered my thinking. What is the law of conservation of energy? It's initial plus initial equals final plus final. I don't even have to put them in the same order as long as I have initial plus initial equals final plus final. I used to make kids memorize this because they used to have to memorize it for the old provincial exam. I've put it on your formula sheet, but it's initial plus initial equals final plus final. Joe, are any of these zeros? Let's do kinetic energy first. Are we ever at rest? And if so, initial or final? Where? Final? You're telling me that the coaster is going to be stopped at the bottom of the hill? I don't think it's going to be. In fact, I think it's going to be going faster. Psst. What does it say we can assume? So which of these is 0? Right? Yeah, yeah, yeah. Potential energy is going to be 0 when we're on the ground. Are we ever on the ground? And if so, initial or final? And so to try and do this with vectors and angles, very difficult. But with a scalar approach, potential energy, that's going to be mgh initial, and kinetic energy, that's going to be a half mv final squared. Joe, have you been on a roller coaster before? Before you got on, did they make you step on a scale? Did they have to separate little people and tall people and big people? Can little kids and grown-ups go on this ride? Why? Mass cancels. It's not that there's no mass. Mass cancels. What are we trying to find? speed technically because we're in scalarville. Um, you can either divide by zero point 0.5 square root. I'm going to, instead of dividing by 0.5, I'm going to times by 2 times by 2. I'm going to get VF squared equals 2GH initial. How'd I get rid of a squared? Square root. It's going to be the square root of 2 times 9.8 times, what was the height? 18. Crunch that, Joe. Let me know what you get. 18.8, is that correct? Units? Good. Could you do me a favor? I'd like to know how fast that is in kilometers per hour. Could you times that by 3.6? Answer button times 3.6. What is that in kilometers per hour? Okay, that's an okay coaster. I'll stand in line for like 25 minutes maybe for that, but I'm not standing in line for an hour. C plus coaster. I've been on faster. Been on slower, but I've been on faster. Now that would be if that was the first hill and we were coming over you come over the first hill in real life with a tiny bit of kinetic energy, but it's close to zero, and so often we'll just ignore that little first bit. Supposing we came over that hill at 22 meters per second, now how fast will it be going? Okay, Gibson, what's B asking me to find? Is there a change in height? Is there a change in speed? Is there a yucky curvy path? You know what my best approach is going to be here? The law of conservation of energy. You don't have to do the echoes. So it's going to be, in fact, the same thing we just wrote. K E initial plus P E initial equals K E final plus P E final. Do they want me to include heat? No, it says ignore friction. Which of these are zero this time, folks? Or is it none of them? Yeah, I think we still end up on the ground. I think we can still do that, but we're not starting at rest this time. Okay. So we're going to get a half mv initial squared plus mgh initial equals a half mv final squared. Gibson, have you been on a roller coaster before? Before you went on the coaster, did they make you step on the scale? Why not? Oh, little kids and grown-ups can go on this ride? What are we trying to find? I would have no problem, don't write this down. I would have no problem if you went divide by 0.5 square root. To a math nerd, dividing by a decimal is just yucky manners. I'm going to go times by 2, times by 2, times by 2, so those 1/2s cancel. And also because then I get my old friend, I get VI squared plus 2GH equals VF squared. I get VF squared equals VI squared plus 2AD in disguise. It's kind of a check, lets me know I probably did this right. And then I would square root. It's going to be the square root of 22 squared plus 2 times 9.8 times 18. Crunch that, see what you get. I'll probably do what's inside the square root first. Square root answer button. Gibson, I got 28.9. Okay, could you multiply that by 3.6? How many kilometers per hour is that? Sorry? That's better. That'll stand in line for 45 minutes or an hour, especially if I got something I can read on my phone or whatever, or I'm with friends and I can just chill. I've been on better and faster. So I'm not standing in line for 2 hours for this, but yeah, maybe for an hour. C. Suppose the roller coaster is only traveling at 25 meters per second. Oh, in part B, so we'll use our numbers from part B, but instead of traveling 28.9, it's only traveling 25 meters per second. How much energy is lost to heat? Well, here, Alfie, change in height, change in speed, yucky, curvy path, and they mentioned heat. It's going to be conservation of energy, G. But I also need to include heat. Jacob, I think PEF is still 0, but I don't think anything else is. Because part B, we started with some kinetic energy, we started up high, and we finished with some kinetic energy according to part C. Alfie, how would I get the heat by itself? I agree. Heat is going to be KE initial plus PE initial minus KE final. It's going to be a half M V initial squared plus M G H initial minus a half M V final squared. Alfie, does an M cancel here? Why not? You're correct. Why not? What doesn't have an M in it? Heat. Okay. So we fibbed a bit to Gibson where we said the masses cancel, but if I can, Gibson, keep heat small by greasing it down, I can make the masses negligible. An empty coaster and a full coaster will make it through with plenty of safety margin on either side. I wonder if I can go straight to number. Oh, what was the mass? 255. Okay, so I think I got my numbers now. Heat is going to be zero point 0.5 times 255 times 22 squared plus 255 times 9.8. I think it was times 18 minus 0.5 times 255 times how fast were we going? 25 squared, not 28.9. I think by a fluke, this almost works out evenly. Or I might be misremembering. I didn't do this one in my head. Do you get 27,004.5 or something like that? I just remembered because it's not often something this complicated works out that nice. So I was okay. So about 20,000 joules of heat. By the way, Alfie, if you knew how long the track was, you could also figure out the average friction force by using work done by heat is the force of friction times distance divided by the distance, and that would tell you the average friction force. Oh, you know what? I think I looked at example 4, part B. I'll bet you that's what we're going to do here. I like example 4. I like example 4. Cart and rider start from rest. Hey, that's nice. On a 20-meter high ramp. Okay. Caden, what does A want me to find? Now, energy lost to heat. Is it asking how much work? Say no. So what would I do? Is there a change in height in this question? Is there a change in speed in this question? Is there a yucky curvy path? No, but do they mention heat? Yeah, I probably want to use conservation of energy. So it's going to be initial plus initial equals final plus final plus heat. Once you've written that down, Caden, are any of these zeros? Oh, that's nice. How would I get the heat by itself? So heat is going to be mgh final minus a half m v initial, v final squared. And mgh initial. Wow, did I botch my initials and my finals pretty good there, didn't I? MGH initial, a half MV final squared. Okay. Heat is going to be, oh, mass does not cancel this time. What did they say? 75 and 20. 75 times 9.8 times 20 minus 0.5 times 75 times 15 squared. Once you've written that out, go to your calculator. Let me know what you get. Again, I haven't done this one in my head, but I also remember I think this one was a nice unusual answer. I think it was 6262.5 or 4 or something like that. Probably 0.5. Is that what you got, Caden? 6262.5? Now, if I reported this answer, I'd do my typical 3 sig figs, but I wrote down the full answer because I thought to myself, I might need that for part B. Aaron, what's part B want me to find? My first thought, don't write this down, but anytime they say what's the force of friction, my first thought is, well, it's mu times the normal force. Did they give me mu? Did they give me a coefficient of friction in the question? No. So I would probably abandon this. Now, I could figure out the normal force. To figure out the normal force, I would need theta, but I can figure that out by going opposite hypotenuse. I think theta is going to be shift sine of 20 over 60. So I could get theta, and then I would say, I don't know the normal force. It's going to be the same as perpendicular of cosine. It would be mg cos. I could figure that out, but I'm still stuck with no mu. So then I might say to myself, Aaron, what did I find in part A? Heat is the work done by friction. Heat equals the work done by friction. What was the heat? 62, 62.5. How do I find work? Well, if it's got a force in it, work is force times distance. Which force? Friction. There's my aha. How would I get friction by itself? Aaron, my friend. Yep. Friction is going to be 62, 62.5 divided by, which D, the 20 or the 60? Well, the force and the distance have to be in the same direction. I saw Presley go kind of like this. I think, yeah. So we're going to be using the 60, not the 20. So you can go answer button divided by 60. I don't know. Well, it's going to be really close to 100. I can tell you that because it's almost 6,000 divided by 60. Probably a little more than 100, 103, 104 ballpark. So I'll call it 104 newtons. By the way, I think in your ultimate review, there's a scholarship question that starts out like this, but it doesn't ask how much heat. It doesn't ask what's the average force of friction. It just asks what's mu, find the coefficient of friction. And you would have to find the heat, find the average force of friction, find angle theta, and you can find the normal force, and then mu would be friction divided by the normal force. It's actually not that tough. It's a lot of steps, and you got to see it all. Rube Goldberg machines are great examples of energy transformations. What's a Rube Goldberg machine? I think I introduced this to you last year, but for my new students, Rube Goldberg was a cartoonist. I think he did illustrations for the Saturday Evening Post in the 1920s and 30s. He would often do their back cover, and he would build elaborate chain reaction machines to perform simple tasks. So, Aaron, the task might be making toast in the morning for breakfast, and you would pull a lever, which would make a ball roll down a hill, which would bump a bird cage, which would open the door, making the bird fly out, which would start pecking on something across the, and you would just have all these things happening, and eventually toast would pop out of the toaster. I love a good Rube Goldberg machine. Here's one. Let's see, Mr. Dueck. Put your pencils down and look up. I don't think I can put this one on YouTube, unfortunately. A bouncing ball is a great example of the law of conservation of energy, G. So I got to talk a little louder for people that are on YouTube because I moved away from my computer. At the top of its bounce, what type of energy does the ball have? Okay. What about at the bottom of its bounce? What type of energy does it have? Kinetic. I notice the ball loses height on each bounce. Does that violate the law of conservation of energy? How so, Jesse? Okay. So at the top of the bounce, what did we say? It has PE, gravitational potential energy. At the bottom, it has kinetic energy. Does this violate the law of CV? No. Ball, or let's just say this. Energy is lost to heat and sound. Is it possible if I drop a ball for the ball to bounce higher than it was originally dropped? And the answer is no, unless there is an outside source of energy. And so I showed my physics 11s from last year a nice trick. I got to pause the video. That's a nice toy. Sorry for those of you on YouTube that can't see the toy that I just brought out. You'll just have to use your imagination. There's a video stacked ball drop. I showed you this last year. I'm going to show you a different video instead. I think I have time. But first, what's the homework? Here's what I assigned my block E's. Number one, and you can state it or just write it, but I'm trying to make sure you've wrapped your brain around it. Number two is good. Number three, we're going to do together. It says this is the side view of a roller coaster. Why won't this roller coaster work? What's the problem here? Tony, where? Can you be more specific, please? Okay, this second hill is a problem. So if you're redesigning, you got two options. You either got to drop this hill, or you need to make sure that this has some kinetic energy here. If it's coming over that first hill with speed, then you can go over a taller hill. And I've been on some coasters where you go over a smaller hill, then you go up a bigger hill to lose some of that energy. I've done that before. But yeah, as it is, this is not going to work. Okay, four is okay. 5 and 6 are good. You can cross out 7. 8 is good. You can cross out 9, 10, 11. 12 is good. Rockets are great examples of conservation of energy. Where do the rockets store their initial energy? Yeah, chemical energy, just a rocket engine. Yep. You can cross out 13. 14 is good. Okay. Pause the video.